So in this part of section 6.4, we're just going to expand on our previous work with the second fundamental theorem of calculus and look to see what happens when one of our limits of integration is not just an x, but it's some function of x. So recall that our second fundamental theorem of calculus said that if you do the derivative of the integral from a to x of f of t dt, that you get just f of x. Remember, we said in general all you're doing is you're replacing your x's in for your t's to get f of x. So now we're going to try to discover what happens when your function or your upper limit is not just an x, but it's a function in terms of x. So we'll do this like we did previously. We'll go ahead and work these out the long way by integrating and then taking the derivative. So the integral of cosine of t would be sine of t, but that gets evaluated at x squared and 2. Well, that's going to be the sine of x squared minus the sine of 2, but then I'm going to take the derivative of that with respect to x. Well, the derivative of the sine of x squared would be cosine of x squared times, chain rule says to take the derivative of x squared, which would be 2x. Then we would have minus the derivative of the sine of 2, but that's just 0. So our final answer is 2x cosine of x squared. If I do the same thing or same process for the next problem, the integral of e to the 2x would be e to the 2x times a half, but then that's going to be evaluated at the natural log of x and at 2. But that's 1/2 e to the 2 natural log of x minus 1/2 e to the 4. But then I'm going to take the derivative of that. So the derivative of 1/2 e to the 2 natural log of x would be 1/2 e to the 2 natural log of x times the derivative of 2 natural log of x, which is 2 times 1 over x, minus, and then the derivative of 1/2 e to the 4th would be 0. And now simplifying, the 1/2 and the 2 would cancel, and we're left with just 1 over x times e to the 2 natural log of x. Now previously we said that all we had to do was substitute in our x for our t's. So it would be nice if all we had to do now was substitute in our x squared for our t's. Well, if we did that, we would get the cosine of x squared, which is part of the answer, but then there's this 2x that we haven't accounted for. But if I take the derivative of x squared, I get times 2x, which is what we have here. So let's try that same process with the next problem. Let's put in the natural log of x, and these should have been t's instead of x's here. So we'll put in the natural log of x and get e to the 2 natural log of x. But we have a 1 over x in the front here that we've not accounted for, but that would be the derivative of the natural log of x. So now let's try to generalize this. Say we're taking the derivative of the integral from a to g of x, where g is some function in terms of x, of f of t dt. Okay, we're going to substitute in the g of x for the t's and get f of g of x, but then we're going to multiply by the derivative of what we substituted in, which would be g prime of x. So let's look at an example to make sure we've got all this together now and not work it out the long way. So we've got the derivative of the integral, let's say from 4 to e to the 5x, and we want to do sine of 3t dt. So we want to substitute in the 5x for the t's, the e to the 5x for the t's, and that's going to give me the sine of 3 e to the 5x, but then we're going to take the derivative of what we substituted in, which was e to the 5x. So the derivative of e to the 5x is e to the 5x times 5. So our final answer would be 5 e to the 5x times the sine of 3 e to the 5x.